What you're looking at is Boeing's vision for the future. This is an initial concept of our hypersonic military aircraft. This model gives you an idea of what we are working on. One day, this aircraft or something similar could be flying at speeds of up to 3,400 miles per hour. That's 5 times the speed of sound. Hey there, I'm Adam Mertz with Boeing Communications, and joining me is Hypersonics research expert Kevin Bocut. And Kevin, just so everyone knows, you are an actual rocket scientist.
I am a rocket scientist. Kind of fun to throw that out there sometimes.
It is. Yeah. So we are talking rocket science. What we're looking at here is our initial design concept of a hypersonic vehicle. Talk to me a little bit about this, the concept, and also for people out there, what exactly is a hypersonic?
Yeah, what does hypersonic mean? Well, most people understand supersonic, breaking the sound barrier, going faster than the speed of sound. So what's hypersonic? Well, it's not a fine line. We typically refer to it as about Mach 5. To gain an appreciation for that, think of having a solid. If you make it warm enough, it'll melt into a liquid. Make it warmer, it turns into a gas. Make it even hotter, the molecules break down. Eventually, the electrons will strip off and become a plasma. Well, at Mach 5, the air starts getting so hot from friction, from shock waves, that it starts to break down. It starts to change chemically. It might break oxygen down into oxygen atoms, things like that. So it changes the nature of the flow. That's what hypersonic is. Want me to tell you a little bit about the airplane?
Yeah, okay. Definitely. Walk us through why it's designed the way it's designed.
You bet. Yeah, it obviously looks quite a bit different than what you would consider a normal airplane to be. One of the key differences is what it's made out of. When you're traveling that fast, friction causes the surface to become very, very hot, over 1,000 degrees, sometimes well over 1,000 degrees, depending on how fast you're going. So you can't make it out of aluminum. You have to make it out of more exotic materials. For example, at about 1,000 degrees, you can use titanium. Beyond that, you can use nickel-based alloys, something called Inconel, up to about 1,500 degrees. Beyond that, you have to go to ceramic materials, things made out of carbon and silicon and aluminum oxides, combinations of those things, similar to what was used on the space shuttle, but much stronger and more robust, more durable. So that's one key difference. The other key difference is, look at how sleek it is. All of the angles to the flow are very shallow, and that's to reduce drag. A very important thing when you're flying this fast, because it creates a lot of drag. These shock waves create a lot of drag, so it's very sleek, very slender. Another thing, one of the questions that came up before the broadcast from Facebook was this inspired by a dolphin?
It kind of looks like a dolphin, like it's going to glide across the air.
Yeah. So the answer is no, but there's a little bit of an oblique connection here. So dolphins, you might have seen, people probably seen dolphins ride waves. Well, my sons are avid surfers. We're in California, we got to surf, right? They're on the high school surf team and everything. So one of my boys once was in a contest, he's surfing, and a dolphin was in the wave right behind him, surfing that wave with him, which is pretty cool. Well, this thing also rides waves, believe it or not. It rides a shock wave. So this wing is shaped to ride on the shock wave it generates, which makes it generate more efficient lift. And we call that a wave rider, okay? Another key difference, a really big difference, is the engine. Looking under here, you can see where the engines are. The inlet's up front, in the back there's a nozzle. Well, the problem is normal jet engines have what's called turbo machinery inside of them, blades. Fan blades, compressor blades, turbine blades. If I go Mach 5 or even Mach 4, those blades are going to get so hot they're going to melt. You can't have them in the engine. But it turns out you don't need them in the engine. Just the motion of the vehicle through the air will compress the air with shock waves. You don't need compressor blades, so you can't have them. And in fact, you don't need them. So this employs an engine called a Scramjet, or supersonic combustion ramjet engine. But a Scramjet has to be moving to work, so it also employs a turbine engine. It's got a combined cycle engine. It's taking 2 engines, blending them together in special, very difficult ways to make one work up to Mach 2 to 3, the other one pick up and work after that speed.
So what you're looking at is a concept for a military type aircraft. Well, yes. What are the applications for hypersonic aircrafts? What could they be used for? What's the future for that?
Well, one is the military application. So let's say you have a rogue country and they're getting ready to launch a nuclear weapon. You got to know that that's going to happen. You got to know where it is so that you can attack it, basically. An airplane like this can move so fast and so high, it can do that kind of a spy mission, right? Other things you could do is just fly fast, like on an airliner, getting anywhere in the world between 1 and 3 hours. Imagine that. Right now, if you're flying across the ocean, it'll take 8, maybe 16 hours, a really long time. Imagine if you could do that in 1, 2, or 3 hours. Pretty cool. There's one more thing that kind of excites me. If you've got an airplane like this that takes you up to that highest speed, you could basically mount another airplane on its back, right? And then at Mach 5, you'd separate it. That one might kick on its Scramjet and accelerate up to rocket speed.
It's essentially launching it.
It's launching it. It's getting a head start. And if both of those are completely reusable and operate like an airplane, now you go from rocketry, where we might throw away the rocket, costs a lot of money, to you're flying routinely in and out of space in a space plane.
Now, one of the great things about being on Facebook Live is we can take your questions at home. So certainly, if you have some, put them in the comments section. We're already starting to get a couple of them. Specifically, you know, talk about how this compares to the Concorde in terms of fuel consumption when you're talking about a hypersonic aircraft.
The faster you go in general, the more fuel you're going to use. So the Concorde used more fuel than a subsonic airplane. This airplane will use more fuel possibly than a Concorde. We've got a lot of modern technology today. Engine technology has evolved. Our ability to design these has evolved. We use computers and simulations. So we can probably design this to fly hypersonically for less fuel. In fact, I know we can for less fuel than a Concorde use. But it is going to use more fuel than a subsonic airplane. What that means is it's going to be larger for the same number of passengers. It is going to cost a little more and take more fuel. But it's a trade-off, right? So it's speed versus, you know, the cost of getting that speed. If we stuck with, you know, we don't want to pay for speed, we'd still be walking and riding horses.
What I love about this is that it's not just speed, because this goes about, in theory, you're talking 5 times the speed of sound, but also the height at which this type of aircraft will be traveling. Talk to me about that.
Yeah, the faster you go, basically the higher you have to fly, because the pressure would be too high otherwise. So at Mach 5, you're going to be somewhere pretty near 100,000 feet. So think about it. That if you've ever seen one of these folks that'll take a high-altitude balloon, float it up to 100,000 feet with a camera, think of what you see. You see the black space above you. You see the curvature of the Earth below you. It'd be a really neat ride to have that view while you're flying across the ocean.
Compare that to a regular airplane ride.
Yeah, well, a regular airplane ride, you're going to be 30, 40,000 feet, so you're 1/3 the altitude. You're much higher. Other than that, it really won't feel different. Some people say, well, how can a human body travel that fast? But we don't feel speed. We go routinely, astronauts go into orbit, they're going 17,500 miles an hour. You don't feel speed, you feel acceleration. And an air breather like this is not like a rocket engine that's going to kick you in the pants and really accelerate you hard. It's like an airplane. So it's going to feel like an airplane taking off. It's just that phase is going to last longer. You're going to be pushed in your seat about 1/3 of a G for a few minutes until you get to 100,000 feet in Mach 5.
When we talk about this type of technology, we don't have a demonstrator yet. We're still putting together the concepts like this one here for a military application. But how far off in the future would something like this be feasible?
Well, for an operational vehicle, we could do it in 10 to 20 years. But a demonstration vehicle, something we just demonstrate the technology, we really could do that in 5 to 6 years.
Now, a question from Joseph at home. He wants to know, how do you mitigate the impacts of the energy from shockwaves when you're traveling this fast?
Well, the vehicle does create shockwaves, and that compresses the air, and it actually amplifies the amount of heating. So one way is we have to just make it out of hot materials or otherwise manage that heat. Other than that, it creates drag, so the engine has to create more thrust to counteract that drag.
And here at Boeing, we've been doing this research for 6 decades.
6 decades.
And this has been your career's work. Talk to me about that. Yeah.
Half of that.
Walk me through some of the stuff that you've done, those enabling technologies to get us to the point where we're at now.
Yeah, okay. Well, yeah, Boeing has done this for 60 years. Hypersonics, flying hypersonically. It goes back to the 1950s with the X-15 experimental rocket plane. We built the space shuttle that went Mach 25. And then in 2004 was the very first time, though, we switched from rocket power to this air-breathing scramjet power. And that's very meaningful because an air breather just uses the air in the atmosphere to burn fuel. A rocket has to carry all that oxidizer with it. And it's a massive amount. It's 6 to 8 times the mass of the fuel is the oxidizer, like liquid oxygen. So back in 2004, for the first time, we flew a scramjet engine and proved it worked on the NASA X-43, which Boeing helped them do. A few years later, we flew the X-51, which was a little bit different. It used, instead of hydrogen fuel, it used normal jet fuel. So those are the key differences.
If you're just joining us, what you're looking at here is a concept for a hypersonic aircraft that Boeing is working on. This is for a military application. I'm joined with Kevin Bocut, who is one of our foremost experts on this topic. Some of the questions we're getting from folks who are seeing this at home, we're looking at a model, which we're standing by. But when it's fully developed, what are some like the specifications? How big would this be? Give people an idea.
Well, it depends. A demonstrator vehicle doesn't carry people in it. You're just demonstrating the technology. It might be about the size of an F-16. Something that's a large spy plane would be, about the size of an SR-71. If it carries people, it's going to be, depending on the number of people. So it could be as large as a 737 if it's carrying enough people, or smaller if it's a business jet.
One of the things we should point out, though, that this would certainly, the technology would more than likely be used for military uses first, correct?
Initially, yes. Yeah, that's most likely. It takes a long time to mature this technology so it's mature enough, safe enough, ready that it could carry people, right? Especially commercial passenger type people. So military applications are going to come first. Certainly.
And certainly that's 10 to 20 years in advance. Right now we're just exploring the concepts and developing that technology.
Correct.
Why does this take so long? Some people might think, hey, we could do all these great things, but this type of technology takes a lot of time.
It does. It's mainly because it's really hard.
It's rocket science.
It's rocket science. It's not easy. The idea for a scramjet, supersonic combustion, came about. It was devised in the 1950s. And basically the idea behind it was, again, I mentioned that you can't have turbo machinery in the engine, right? Well, if you fly up to about Mach 5 or 6, you can use something called a ramjet, which actually slows the flow down until it's going less than the speed of sound. But as you go faster and faster, eventually that creates too much pressure, too much temperature in the air, so we switched over to the scramjet. We let the flow stay supersonic.
And for people at home, what exactly is a scramjet engine?
A supersonic combustion ramjet. So a ramjet is an engine that just uses its motion to compress the air. The supersonic part means everywhere inside the engine, the flow is still supersonic. So think about that a little bit. If you've ever walked outside and lit a match in the breeze, it's really hard to do. A light breeze, it'll blow out the match. Think about air going a couple thousand miles per hour inside of this duct, and you're trying to inject fuel, ignite it, and get it to burn. The air is in there for 1 millisecond. In 1 millisecond, you have to do all that, get it to burn, and that's why it's been so hard. It's taken decades to master that technology, to figure out how do you shape it, and how do we test it, how do we prove it. We finally got to that point in 2004.
Looking at the model, where would the engine be on this?
Well, it's inside these things down here. These are called nacelles. So again, it's a combination of turbine engines and scramjet engines inside there. Can't tell you a lot about the details, but they're inside that nacelle.
We're talking about the materials that would go into this. What would it be made up of when eventually it were evolved to an actual aircraft?
A combination of things. Nickel-based metals. So there's a material called Inconel. You pull a nickel out of your pocket, it's got some nickel in it. So nickel is a high-temperature metal. It's good to about 1,500 degrees Fahrenheit. So that's one choice we have to make things. There's some titanium pieces that could be made out of it as well. And then if you get to temperatures much above 1,500 degrees, you go to what's called a ceramic material. A glass is a ceramic, okay? And if you look at the space shuttle tiles, they were actually made out of a type of glass. But they were delicate. So today what we've done over the years since Space Shuttle is invest in how do you make something out of a ceramic that's tough, that's really strong, and that won't easily break. And those are the kinds of things that we will make these airplanes out of.
One of the things I want to go back to is the speed. 5 times the speed of sound. Give people an idea of how quickly you can get around the world if you're going that fast. I think the comparison you gave yesterday, it's twice the speed of a speeding bullet.
Yeah, it's more than twice the speed.
Twice.
2.5 times the speed of a speeding bullet. It's more than twice as fast as the Concorde. So basically you can get anywhere in the world in 1 hour across the Atlantic, 2 hours across the Pacific, pretty much anywhere between 2 points in 1 to 3 hours.
A question from Trevor at home. How do you convert from turbomechanical to scramjet in flight?
That's a good question. So there's one set of inlets that actually feeds both engines. So when you're at low speed, the air is going through the turbo machinery, and And then at some point, you actually have to change the inlet configuration with variable geometry, basically open doors, close doors, to divert the air into the other engine.
It's a good question. Going back to the design of this, too, earlier you compared it to a wave glider.
A wave rider.
A wave rider.
Wave rider, yes.
Riding the Shockwaves.
Yes.
Walk us back through why it's designed the way that it is. Because certainly there are reasons why it looks this way, looks so sleek.
Yeah. Well, the main thing is you got to make it very, very sleek, very low drag. So if you went and stood at any point on the vehicle and looked at the flow coming at you, the flow's hitting the surface at a very, very shallow angle. That reduces drag. If you look at from above, you're going to see this kind of a wing shape, and this is a wave rider, so it actually creates a shock wave, and it rides on that shock wave, which basically is a low drag way of creating lift. Then you might ask, well, why do the wings flare out here? Well, this airplane has to take off, it has to land, it has to have enough wing to do that, and that's what these aft wing surfaces do here. And actually there's some interesting things for if you've ever seen, I don't know, a tornado or a vortex. These leading edges are shaped to actually create these vortices on top of the wing that actually suck it up and help increase its lift. It's kind of a neat way to boost lift.
The future. What do you foresee? What's your vision for hypersonic aircrafts? What should people expect in the next couple of decades?
Mainly that we have one that we can get. We're not hampered by just traveling around the world at less than the speed of sound. That maybe in 10 to 20 years we can go get on one of these and travel across the ocean in a couple hours. Imagine waking up and maybe having breakfast, go hop in the plane, fly to Asia, have a meeting for a couple hours, come back and land and sleep in your own bed that very same day. So 1 day international travel. And the other one is flying into space just routinely. What if the average person could go hop in a space plane, take off, and go out into orbit and maybe hang out on the space station? Those are two of my dreams and visions for the future.
And one of the things that comes with is balancing the cost
yes.
to make this affordable and worth doing. Discuss that.
Well, it's always a trade-off, and an airplane like this is going to use more fuel. It has more drag. The engines use more fuel. They're less efficient, so it's going to be bigger. It's going to cost more. A plane ticket is going to cost more. How much, we don't know. That takes a lot of study. It takes a lot of, looking at the market and figuring out what that costs. But it's going to be more expensive. So it comes down to what's the value of speed. What's it worth paying to go internationally in 1 day or in a couple hours instead of taking an entire day just to get to your destination?
What sort of technologies are we working on right now to get to that point? What would make this different?
Well, I mentioned earlier that it's made out of more exotic materials, so there's a lot of work going into developing the materials. I saw one of the questions, are they composite materials? The ceramics are composite materials. So one example of that is you take carbon fiber. Now we're familiar with normal graphite composites, right? We got carbon fibers and an epoxy resin. That's called the matrix. Well, epoxy resin is going to melt, after a few hundred degrees, so we can't use it. What we use instead is a carbon matrix. So it's called carbon fibers with a carbon matrix that can withstand like 2,500 degrees Fahrenheit. Or you might have carbon fibers with a silicon carbide matrix. Or you might use what we call oxides, these materials that are made out of oxides of other materials, like aluminum oxide is actually a high temperature material, not aluminum itself, but alumina or aluminum oxide. So we make compounds or composites of these materials that can not only withstand the temperatures but are robust. You won't just tap them and a chip falls off of them. They can be as durable maybe as a metal.
Another question from our viewers on Facebook: why use tails, vertical stabilizers? Shouldn't all wing designs be best for drag?
The answer is yes, it would be, and maybe we'll see that trend. You'll notice that subsonic airplanes today, some of them are tailless, so that's an area we're pushing into, is tailless vehicles. I think initially hypersonics we're going to need the extra stability until we've figured out how to reduce uncertainty and make sure we understand how we fly them. We're going to want them for stability and control. But I do foresee a day where we might be able to eliminate them at hypersonic. And you're right, it'll reduce drag, reduce weight. It's a benefit to do that. It's just we got to stepwise, we've got to step up to that.
And that's all stuff we're working on. The timeline is 10 to 20 years
yes.
before something like this comes to fruition then.
It is, and so materials is one. The engines, already, the idea of a scramjet in the 1950s, and think of, count the decades. 2004, we finally put one on a flying machine, the X-43A, and proved that a scramjet really works. It was theory up till then. We could put it in a wind tunnel, but there's things about the wind tunnel air that isn't exactly simulating flight. It's also difficult in a wind tunnel to actually measure the thrust for a lot of different technical reasons. So we really weren't 100% sure that when we put a scramjet on an airplane it was going to create thrust, but we proved that it did.
And this concept is for military applications. What are some of those applications that it could be used for by militaries?
Well, basically, it's a spy plane. That would be one of the premier applications is, we have satellites that do that kind of work, but they have periodic orbits, right? They can only be, and so if you absolutely had to know what a foe is doing and do it quickly, you could fly. And we've got airplanes too, right? Global Hawk, we've got ISR type, but if you want to get there quick, and it's very critical that it's quick because things can happen in a timeline, use something like this to go, take pictures and find things, that kind of stuff.
For you personally, to see this come, decades and decades of work, how do you feel to see, at least see the end zone? You're moving forward, you're seeing this technology evolve. What's it like for you personally since you've worked on this your entire life?
Yeah, actually it's hard to explain, it's hard to describe. So when I was a kid, 11 years old, I was really interested in how things worked, and I would study them. I'd even build them sometimes, take them to class, show my classmates how they work. That led me to a fascination with fly. How do things fly? That led me to building model airplanes, like remote control airplanes, which led me to college and an aerospace engineering degree, which I continued on to my PhD. My PhD work was in optimized hypersonic aerodynamic shapes. And I actually figured out a way to optimize these wave riders. So what I did in my PhD program was design wing shapes like this. So I was brand new student, brand new graduate, headed to work for then Rockwell International, which became part of Boeing in 1997. And I got to work for 8 years on the National Aerospace Plane. And that was an attempt to build that kind of that space plane I was talking about. We didn't succeed then. We were a little before our time. But since then, I've been just working on, and that was my dream. My dream was to actually help design, participate in the design of a hypersonic airplane and see it fly. So when I first saw, now the X-51, actually, I'm the father of the X-51. This was my baby in 1995. I came up with the design for it, and then go forward 15 or so years, and in 2010, I got to see it fly, and that's just an amazing feeling to spend a couple of decades, a dream of yours, and then finally see that dream become reality. It's really hard to explain how exciting that is. I was very nervous, very scared, but when it happened, it's hard to compare that feeling of what I felt.
For those of you watching, if you have more questions for Kevin or about our hypersonic research here at Boeing or this concept for a hypersonic aircraft, be sure to leave them in the comments. We're going to try to answer some of those after we sign off. But again, thanks so much for joining us. Kevin's going to stick around and we're going to try to answer some of those questions for you on Facebook. Take care.